So this is just the last part of lesson 2, and this is estimating a sample size. Okay, so that is our goal. So this is before creating the confidence interval. So we know how to create a confidence interval. We're talking about even before that. When researchers go out to collect data, they usually have an idea of what kind of confidence interval they want at the end of the day, right? Like they know kind of how confident they want to be, like 90% is enough, or maybe 95 or 98. And they also kind of want to know at a certain width for their confidence interval. They know like how precise they want their confidence interval to be. Okay. So with those in mind, they're going to go out and choose a certain sample size to get a certain margin of error and a certain width to their confidence interval. Okay, so that's what we're going to learn today, how to choose that sample size. All right, so first focusing on that formula that we went over during homework, so perfect. And this part, remember, is the margin of error. All right, this part is the margin of error. So we want to figure out what sample size n will give me a certain margin of error. Okay, what sample size n? We're going to be solving for n today. All right, so we're just going to focus on this part, the margin of error of our confidence interval formula. Okay. So now the first question is, well, if we have our unknown to be n, that means we need to plug in stuff for z star, and we need to plug in stuff for p hat and q hat. The problem is, well, we don't know what p is, right? That's the whole point of creating a confidence interval, is because, well, we don't know what p is. That's why we're trying to capture it with our confidence interval. So the question is, well, what do we plug in for p then in this formula? All right, so when we don't know what p is, we use p hat. But now the thing is, well, we haven't collected a sample yet, so we can't do that either. Unless we have an idea. If we have an idea of what p hat is, we can plug that in. But let's say we don't have any idea what p could be. What you actually want to plug in for p is 0.5. All right, so when you have no idea what p or p hat is, the most conservative estimate of p is going to be 0.5. Okay, now let me show you why. The reason why that is the most conservative is think about the product of p and q, right? We want the largest value that can be. Well, if p is 0.5, that means q is 0.5, which gives you a product of 0.25. And if you step away from that, if p, let's say, is 0.4, q then is 0.6, notice it gets lower and lower as p deviates from 0.5. Even the other way, if p was 0.6, q would be 0.4. That product is still lower, right? So that's why we use p of 0.5, because that is the most conservative estimate that will give us the biggest product in my numerator here. Okay? All right, any questions about that? Using 0.5 as our most conservative estimate of p. All right, cool. So now that we know what we can plug in for p, we also know how to find that z star. That was our lesson from yesterday, right? Using inverse norm, we can find what z star is. We know what to plug in for p and q. They'll be giving us the margin of error, so that just leaves us with n to solve for. All right, so let's try this out. Here we go. Let me get a reader. Billy, can you read this one out for us?
Yeah. In spite of the potential safety hazards, some people would like to have an internet connection in their car. Determine the sample size required to estimate the proportion of adult Americans who would like an internet connection in their car to within 0.03 with a 95% confidence.
Perfect. Thank you, Billy. Speaking of, I heard Tesla had to recall like 135,000 of their cars because their big screens were malfunctioning. So, anyway, that just reminded me of that. Okay, so first thing, 2 within 0.03. This is the margin of error, right? Like yesterday, the weight question, I said, try to guess my weight within 20 pounds. That was how wide your confidence interval was. That was your margin of error. Okay. So, same thing. This 0.03 is your margin of error on the left. And looking at the problem, we have no idea what P might be. So, we should plug in 0.5 in for P, which means Q, which is 1 minus P, is also 0.5. Z star, this is from our lesson yesterday. We do inverse norm of 0.025, and that will give us a Z star of 1.96. Okay? Now that leaves us with just N to solve for. So we use some algebra, all right? Divide both sides by 1.96. You square both sides. You can multiply by N and then divide to solve for N, and you get on your calculator 1067.111. Okay, now here's the thing. With these problems, once you get your answer, and it typically will be a decimal, you should always round up. You should always round up. Even if this is 0.0001, you should still round up. The reason being is if you round down, you will actually just be shy of meeting this criteria of within 0.03. All right, it'll be close, but you'll just be shy. So if you want to make it, you always should round up for your sample size. All right, so your final answer would be 1068. Okay, so that is how you do the problem. Let me go ahead and open up for any questions. Feel free to type it in the chat. Let me know if you guys need any help. So you guys got all this plugged in, right? So within 2%, you have the 0.02. I'm just going to explain it in case somebody just actually doesn't and want to know. 99% confidence, how to get the Z star. Hopefully you guys did inverse norm of, and I even, here's a little trick I do. In my calculator, I actually type 0.01 divided by 2 into my calculator. Just because for me, I tend to make careless mistakes with like how many zeros do I put in. So I know 1% is 0.01 divided by 2 gets me that one tail. So that's a little trick for you guys that you can actually type that into that field and the calculator will do it for you. All right, so that gets me 2.576 for the Z star. All right. No, so now to solve. Okay, first thing I would do to solve is divide both sides by the 2.576. Okay, so I get 0.02 divided by 2.576. And then I'm going to square both sides. 0.5 times 0.5 is 0.25, so I'll go ahead and do that up there too. And then I'm going to square both sides to get rid of the radical. All right, so that gets me 0.02 over 2.576 square is equal to 0.25 over n. All right, and then next, what I'm going to do is I'm going to flip both sides because I want n in the numerator. So I'm going to do the reciprocal. And do a flip of denominator and numerator on both sides. And then I'm going to multiply both sides by the 0.25. Let me do this in a different color. So 0.25, 0.25. All right, So that's what you type into your calculator. So I would do 0.25 parentheses 2.576 divided by 0.02 and parentheses square it. And then this gets you n is 4147.36. All right, but remember, you always need to round up to the nearest whole number. So this 7, I'm going to round up to 4,148 people. And that is your final answer. Okay, how are we doing? Let me know in the chat. Let me know if you have any questions on those steps. All right, so for number 3, this is what I did. So they give you the sample size, they give you the margin of error, they give you the rate, and you're looking for the confidence level. Now, I know the confidence level is linked to Z star, so really that's what I'm looking for. So using my margin of error formula, I plug in everything and just leave Z star to be solved for. All right, so then I divided both sides by that square root thing, and I got a Z star of 1.598. Okay, now if you think about the link between the Z star and the confidence level, right? Negative Z star to positive Z star in the normal model, right, is what cuts off this area. And that area is what percent confidence I will be in this confidence interval. So to find this area, I use normal CDF. So I do normal CDF of negative 1.598 to 1.598. All right, so negative to the positive, mean of 0, standard deviation of 1, and I get 0.89, which means my final answer is I will have a 89% confidence interval. And that is the answer.